Hi everyone, I'm here to talk to you about what we call fshade. It's basically an embedded shader language for our rendering engine. And the basic experience with that is that functional view on shaders gives you really significant benefits when it comes to reuse of things. First of all, what are shaders? I think most of you will be familiar with what shaders are. There's various stages in nowadays hardware. Historically, you had a vertex shader and a fragment shader. Today, there is more involved concepts such as tessellation or geometry shading. And from a high-level point of view, shaders are just pure multi-valued functions, which means they consume multiple inputs and produce multiple outputs. But they have no side effecting things, basically. That changed a little with storage buffers being available in regular shaders. But for now, let's just consider shaders as pure functions. They take inputs and produce the exact same outputs when fed with the exact same inputs. The shaders, we need more than one shader to render something. We need at least two shaders to render something for the vertex and the fragment stage. The others are optional, so each shader is basically associated to a stage or is a program for one of those stages. They can have different kinds of inputs too. There is basically input attributes and uniforms, and also the kinds differ because the vertex basically takes vertices, the geometry shader works on primitives and so on. So why do we even want a new shading language? And the plain answer to that is it's a combinatorial explosion problem. As you see in the little image here, we have, this is a real screenshot from our old repository. You have things like, okay, we need a surface for a shader for a shadow map caster, and the shadow map caster with alpha texture, and the shadow map caster that is animated with alpha textures, and that is not animated or replicated, and so on. So you have about 2,000 different variants of the same shader, just slightly adapted. And there's obviously solutions to that. The classical approach would be to write some what's called Uber shaders, where you have classical if-def cascades where you calibrate what the shader does and compile those, but they don't really scale. If you have 10 different aspects you want to combine, those programs become very unreadable. Another motivation for fshade is what we always wanted in our rendering engine is a programmatic manipulation of shaders. If the rendering engine figures out that there's a lot of shader switches going on, maybe I could unify those two shaders and make it a runtime switch, or make rendering more efficient by changing shader code. And of course, as always, there's multiple target languages. We just implemented a Vulkan backend, and suddenly we need a new shader language, or a new shader language target, which was easy since we had a thing for that. So let's just, for a very short look at shaders. We have two admittedly strange shaders here that take some inputs, produce some outputs, and what I envision, or what we like to produce, is something like that. We want two shaders. We want just to compose our two shaders by basically sequential semantics. We want the color of the, if we compose A with B, we want the color from A to go into B. We want the normal from B to be the output. We want the normal from A to be hidden by the normal of B, and so on. This is basically a multi-argument function composition. We want other things to happen. We want the kind, which is just some random name of an input here, to be automatically passed to the shader B. We want the position, which is an output of shader A, to be automatically passed to the overall output of that system. This basically resembles multi-valued function composition in a sane way, so to speak. So how does this work? Consider those two shader codes. It's just regular GLSL. It's basically very simple. All you need to do is you just need to copy those codes underneath each other. And basically all you now need to do is you need to just adjust the variables, because you have here writing the output position and here writing again the output position, which is obviously not what we wanted. But it can be easily achieved by just introducing some variables and just delaying the writes to the bottom of the shader, and basically that resembles exactly the composition operator we desired. So how did we do that? Basically, F-Shade is an embedded language in F-sharp. F-sharp provides us with what's called quotations. It's basically a reflected variant of the code you write. You can extract for each function, or for some functions, you can extract the code you wrote or the definition of the function, and which spares us the need to write a parser for our own shader language and define a new language. It's just embedded in F-sharp, and the syntax is known, or there is a parser and a compiler and error tracking and all that for F-sharp. So our choice was F-sharp because our renderer is written in F-sharp. Yes, it's embedded in Aardvark, in our rendering engine Harald mentioned before. And basically the concept extends to other languages. You could, for example, use templates, quotes, Haskell's quotes, or other languages that kind of support those quoting mechanisms. And if you're brave enough, you could most likely implement it in C++ using templates. Or you could, if you don't have any of those languages, you could just write a standalone parser for some input language. You could also use GLSL. So what do our shaders look like? Here's a simple example. This is standard diffuse specular lighting. As you see here, we just have a fragment shader, which basically takes some inputs. We have those little annotations here. These are essentially the names the system uses for composing shaders. If you have, you can define custom ones. Those are just some convenience predefined things. And basically, these are the names the whole composition mechanism uses, and some of those have a special semantics, such as position, because each fragment in the stage before the fragment shader needs to emit a position in order to support rasterization. And yes, here you have a code. You see it's just a simple thing, taking a vertex. Here's the annotation that it's a fragment shader, and basically just looks like regular shader code. And yeah, this is a special case. It just returns a color. It could also return another more complicated or involved type. And yes, it's not concerned with anything else. It's not concerned with where this color comes from. It just takes the color and produces a lighting. And our transformation shader, for example, is a little more complicated. As you see here, it basically transforms everything that could possibly be needed by any other shader. So we have normals, binormals, tangents, and all those things. We have directions to a light, directions to a camera, and all of those things need to be transformed with the appropriate matrices, which at the first glance looks a little strange because most often you won't need all of those values. But our system basically for composition of shaders automatically removes all unused inputs transitively through all stages. And so I'll just show you an example here. This is our testing model. It has everything. It has normals, it has normal maps and everything else. And as you see here, if I just these are the two shaders we just wrote that are active, and here you have basically the GLSL output. And I don't know if you can read it, but here you see there is the only two inputs for the whole vertex shader are currently normals and positions, because the simple lighting doesn't need anything else. And the color is actually a uniform color at the moment. So this is a little boring. Let's add some texturing. And as you see here, our vertex shader basically just got an input diffuse color coordinates, which is our name for those standard texture coordinates. They automatically get passed to our fragment shader, here by the vertex shader, which without any transformation. And finally, here in the fragment shader, we have the texture lookup, basically looking up those textures. Okay, this rule here looks a little crappy, so let's add an alpha test. It's just a little shader that basically performs alpha testing on the color. Again, this thing doesn't know where its color comes from. It doesn't know that the color is coming from a texture or an input. So I can just disable the textures again, and as you see, this color obviously is opaque, so this is not, the alpha test doesn't affect it. Then, okay, there's a little more interesting thing. We have a skinning shader, which basically allows us to animate the model. Again, this is just basically a vertex shader that processes all the vertices with a skinned animation. Again, we can still do this without texturing or with texturing. We can also remove the lighting, which is admittedly a little boring. Yes, then there is other things like we have normal mapping, for example. The thing has a pretty normal map. Normal mapping is not at all concerned with the lighting itself. It just is a shader that takes a normal and the texture and produces a new normal, which means when I remove the lighting again and look at my fragment shader, I see that there is no calculation going on because the normal that is produced by the normal mapping shader is not actually used by anything. If I reactivate the lighting, you will see here that here is my normal map lookup, and I have those tangent space constructions here, and all the things get automatically passed through the system. Yeah, it has also a specular map. I don't know if you can see it. Yes, a little. And if we compose all those together, we basically have a nice rendering of the thing. It can also attack. Yeah, and this is basically what F-Shade is really, really good at. We have 7 shaders. I wrote 7 shaders, and I have 128 combinations of those shaders at the moment, which I can just programmatically change. I can add new things. I could, for example, I don't know, I could also replicate the model or have a geometry shader sit on it that does something with the primitives. And yeah, that's basically a very powerful tool. I'll show you another short example. These are just stupid shaders that basically do something really stupid. It just shows a concept. We have 3 geometry shaders. The first one is actually dividing a triangle into 3 triangles like that. The second one just shrinks a triangle, and the third one creates a tetrahedron from a triangle in some weird way. And what we now can do is we can basically use those shaders and compose them all together, which means here on the top, here on the bottom, you have just the plane 2 models being rendered. You could divide the triangles, the center point is rendered in white, and so on. And you can also combine 3 of those geometry shaders, which basically gives you shrink triangles that are subdivided and shrink triangles that are subdivided and extruded and so on. So the concept is quite powerful. Admittedly, those things do not really make sense, but we've already seen things where geometry shader composition is rather crucial. If you have a thing extracting lines from a geometry and then you want to apply thick lines, and you have those pipelines where you want to compose various effects together. So yeah, and other things you could do with such a system, or things we did, we implemented an automatic hardware instancing, which means we can just modify the shader code by transforming uniforms to instance attributes and so on, and the rendering system understands that. So the rendering system can do automatic instancing of things or complex things. You could also, or what we did is basically a single pass stereo rendering, where you also need to modify the shaders accordingly to direct them to the correct eye output. This also works on SLI setups, which is another tweak. Other things like adjusting to a specific platform or specialization, and many more things could be done with such a system. Yeah, some limitations, very short. Our input language has lambda functions. We cannot have lambda functions in GLSL. This is currently a little problem because sometimes lambda functions arise without specifically using lambda functions. Yeah, recursive functions and types don't work in those shader languages, or at least not in GLSL. Dynamic allocation in any sort doesn't work, and yeah, other typical constructs such as references or subtyping simply do not scale to shaders. So that's it from my point. Are there any questions?
What I want to ask, every time you generate a new shader, it has to be sent through the GLSL compiler of the driver, right?
No, actually not. We have a caching for that, but it's just a caching, yes. In principle, yes. If you write a completely novel shader that the system never saw, yes.
Yeah, surely. So you generate a new shader text and it's being sent to the driver to compile it so that it can be run.
Yeah, currently that we have an experimental backend directly producing VRV shaders, but this is not yet completed or anything.
Mm-hmm. Yeah, but that doesn't take a lot of time anyways. Okay.
Okay, let's thanks speaker again.